Section 6.3, Series Solutions. The first two sections of this chapter were dedicated to reminding us of some of the basic properties of series representations of functions. Now that we've reviewed those properties and how we can build series solutions ourselves, how we can manipulate or modify series representations of functions, we're ready to see how series can be used to solve differential equations. First, just to give you some sense of the type of differential equations that we'll be looking at, there are actually quite a few differential equations from physics and engineering that are well known and widely used that have a structure which is very, very similar to the LHCC differential equations we studied in Chapter 3. The one difference, or the one property, that makes these differential equations not fit LHCC form is that the coefficients of all of the y and y prime terms are not necessarily constants. Instead, one or two of the coefficients in many of these equations are polynomials. They're relatively simple polynomials. If we look at the Legendre equation, for example, the coefficient on this y double prime term is just a quadratic. The coefficient on y prime is a linear. Similarly, throughout these several examples that I have provided here, you can readily recognize that the structure is very similar to an LHCC differential equation, except that one or more of the coefficients is some simple polynomial in terms of the independent variable x. For our purposes in this section, we won't spend time deriving or really investigating these equations or the physical situations that they model, but I just wanted to provide this list as to demonstrate several examples of differential equations that have this property that I've just described. As it turns out, when a differential equation has this structure, it is particularly well suited to be solved using the series techniques that we'll demonstrate in this section. In this next paragraph, I very briefly outline the strategy or technique that we'll use to employ series as a method for solving differential equations. Specifically, these are the steps. First, we'll assume our unknown solution function is represented by some generic power series. So this general power series, where I haven't tried to specify what the coefficients need to be, I simply know that the structure will be some coefficient expression times x minus x naught to the n. This is the structure that I am assuming my solution has. Next, I take the necessary derivatives of this unknown solution. In the previous section, we saw how a power series like this can be differentiated. And it's actually a relatively straightforward process because the variable terms are simply polynomial terms. So they're just raised to a constant power. So to differentiate, I just need to bring the power down and subtract one from the power as necessary. Next, we plug the series representations of y and the needed derivatives into our original differential equation. And then lastly, we manipulate the resulting series. Indicate here that we'll have a couple series, so multiple series. And we just manipulate those somehow algebraically or by modifying the index as necessary until we have an acceptable representation of our solution function. Hopefully those steps seem pretty familiar. In fact, this is pretty much the same structure of the technique that we've been using to solve differential equations over and over again since Chapter 3. We assume our solution has a specified form. We plug that into the differential equation. We simplify. What really makes this method distinctive in this chapter is that the solution is assumed to have this series representation. Before we move on to try some examples, there's one key fact that I want to point out. It's kind of an algebraic fact. Just to demonstrate this principle, let's consider the equation ax squared plus bx plus c equals 0. And suppose I wanted to solve this equation. I wanted to find x values. We know, we've solved dozens of these in our mathematical careers, and we know that we can find discrete x values that make this equation true. What I mean by discrete is I mean separate, distinct x values. So you've seen an equation like this, and maybe the solution was x equals -1, x equals 2. So those are two distinct separate x values that make this equation true. And that will always be the case if we are given specified values of the coefficients a, b, and c. So anytime the coefficients a, b, and c are determined or specified, then the x values will be discrete. But suppose I had this same equation and I wanted to kind of flip my perspective. Suppose I didn't necessarily know what the coefficients a, b, and c were. I guess I'm talking about the equation down here now. Suppose I didn't know what these coefficients a, b, and c were, and suppose that I wanted to insist that the equation was true for some interval of x values, not discrete separate x values, not x equals -1, x equals 2, just those two x values, but some entire interval of x values. Imagine somehow that the solution would be true on all x values from 0 to 1. I think it's pretty clear intuitively that the only way to accomplish this would be to force the coefficients in the polynomial to be 0. In the case of our particular quadratic, I would need to force a and b and c to all be 0 in order for the equation to be true for an entire interval of x values. And as I note here, if I were to force a, b, and c to all be 0, then this equation would become true for all x values. And that means it's certainly true for an interval of x values. This is a really core idea in our technique, as you'll see over the next couple of examples. And let me just reiterate, as I've sort of highlighted here, the key idea is that in order for an equation like this, a polynomial set equal to 0, to be true for an interval of x values, we need to force all of the coefficients in that polynomial to equal 0. And I've explained this in terms of a quadratic, but this would clearly be true if my polynomial equation was instead a cubic or a quartic. This would be true for any polynomial. So with that in mind, let's go ahead and try a couple of examples. So in this first example, we're given a differential equation that kind of has this form that I just described, where it's almost an LHCC differential equation. I just have this x coefficient on y prime that prevents me from being able to use the chapter 3 methodology. So instead, as I just highlighted, our technique here will be to assume that my solution has a series representation, find the appropriate derivatives of that series representation, plug those into the differential equation, and then in this case, we'll just kind of see where we can go from there. A key detail in the statement of the problem is that the series solution that we're after should be centered at x0 equals 0. This implies that the series that I'm about to suppose for my solution must have the structure that it's written in the terms of x minus 0 to the nth power, because this 0 here is the center of my series. Of course, it's unnecessary to write x minus 0, so I'll simply write my series in terms of x to the n. Given that detail, I will now suppose that our solution has the form of a generic or general power series. Here my variable terms are x to the n, because as I just pointed out, the center is 0. If instead my center was 1, then these power terms would be x minus 1 to the n, or x minus 2 if my center was 2. So I have to adjust those power terms appropriately. In this case, since it's centered at 0, I just have x to the n. And now this is an unknown function, so I don't know what the coefficients are. Coefficients, as we pointed out in the first 2 lectures in this chapter, the coefficients are what determine the series. So in a sense, our ultimate goal here is to figure out some way of describing what these coefficients are. Because if I can identify or somehow define or compute the coefficients, then I will have effectively identified what this function is. So that's my first step. Suppose that our solution has a specific form. The next step is to identify the necessary derivatives. In my differential equation, I have a y prime and a y double prime. So as we saw in a previous lecture, I can take the derivative of this solution function. I forgot to label that as y prime. There we go. And I can take the derivative of this y function by simply applying the power rule. This is some coefficient times x to the nth power. I know that when I differentiate, I'll bring that power down and I'll subtract 1 from the power. So my derivative will have this structure here as a series. Also, as we saw in previous lectures, when I do that differentiation, it forces my index to increase by 1. If you were to write out the first several terms of this sequence, we know that the n equals 0 term is simply a constant. When I differentiate, that constant term goes to 0. So the first term in this sequence will correspond to n equal to 1. I can repeat that general process and take the derivative of y prime, and I'll get a series representation of y double prime that looks something like this. Once again, I look at this function here. This is x to a power. So if I want to differentiate, I will bring this entire power, this power n minus 1, I'll bring it down as a coefficient. That's why it appears here. And then I'll subtract 1 from that exponent so that instead of n minus 1 in my exponent, I'll have n minus 2. I'll take those ingredients and plug those into our differential equation. That is to say, here in my differential equation where it says y double prime, I will plug in this entire power series. Then I'll have minus 2x times y prime. So for y prime, I will plug in this entire power series, etc. Let's give that a shot. So plugging those ingredients into my differential equation, I get this expression here. Again, you should just verify that this is y double prime minus 2x times y prime plus y equals 0. So now what the heck do I do with this expression? I've got 3 power series, I've got infinitely many terms in each of these. How do I move forward? Our next main goal is to somehow modify each of these series so that we can get them to match up. Notice, for example, that in this first series, the power terms, the variable terms, have the form x to the n minus 2. Whereas in this series, they have the form x to the n minus 1, and in this series, they have x to the n. My primary goal is to modify these series as necessary so that those power terms agree. That will enable me to actually factor those power terms out, or you can think of it as factoring the coefficient off of those power terms, and then I will eventually be able to write a single series on the left-hand side of this equation. So there's a couple things I need to address. First of all, I just noticed that this second series here has this coefficient on it, 2x, negative 2x. Now recall that this series is essentially just a really big polynomial, and so if I had negative 2x times a polynomial, I could distribute this negative 2x into every single term in that polynomial. The negative 2 would simply get multiplied by whatever coefficient was already there, and then the x would combine with the x's that are already there, and all of the powers on x would increase by 1. Let me write out what I think this middle series will turn into. So if I distribute this coefficient into the series, the negative 2 becomes part of the coefficients, and then this x combines with the existing x's, and each of these x terms, its power increases by 1. So instead of it being to the n minus 1, it'll be to the n. Now, based on this series, based on this third series as well, I now see that I'll have x to the n in 2 of those series. So what that means is I'm going to target x to the n as kind of my goal structure or my goal form. And I'm going to modify all of these series as necessary so that, as I mentioned before, those power terms will all agree. Specifically, they'll all have the form x to the n. I kind of luck out with this third series because it already has that structure, so I don't have to make any modifications to this series at all. On my first series, though, I need to increase the value of n by 2 so that this term will be x to the n. As we saw in previous sections, I can make this sort of modification, but there are repercussions throughout the entire series. Specifically, if I want to increase the value of n within the series representation, that will correspond to, or that will imply, that the beginning index must decrease by 2. So when I make that modification, now again, I'm not changing the series. I still should have the exact same series. I'm just, in a sense, describing or formally representing that series in a different way. So when I make those changes, this is how that first series now looks. Remember that this is all set equal to 0. And now I have successfully rewritten each of these series so that they all have the form x to a power. Sorry, x to the same power, specifically x to the n. So now what I want to do, in the limited space I have left, I want to factor out those x to the n terms. There's one additional detail that I have to attend to before I do that. Notice that this first series starts at n equals 0, but the second series starts at n equals 1, and this third series starts at n equals 0. So this seems sort of strange to say, but it's as if this first series has one more term than this second series, and this third series also has one more term. So before I can factor out the x sub n, I need to force all of these series to have the exact same structure. So here's what I'm going to do. The n equals 0 term, the very first term in this series, I'm actually going to peel it off. I'm going to write it separately. Double check that if I plug in n equals 0, I'll get 2 times 1 times a sub 2 times x to the 0th power. So I've just written that here as 2 times 1 times a sub 2. And now the remainder of that series will have the same structure, but it will just start at n equals 1. This second series already starts at n equal to 1, so I don't have to make this type of modification. And now this third series does have that additional term, so I will once again peel off that n equals 0 term and then write the n equals 1 through infinity terms in this sigma form. And I'm definitely going to need more room, so I'm going to add a blank page to this document quick. So now I have successfully restructured all of the 3 series so that they all start with the same index and they all have the exact same power term. I'll move these extra terms that I peeled off, I'll move those out front, and then from these 3 series I will now factor out the x to the n. So again, I'll be writing these 3 series as a single series, and I'm going to factor out the x to the n. So when I factor that out of this first series, I'm left with this coefficient expression. And then from the second series, I have this coefficient expression. From the third series, I have this coefficient expression. So if I was to write out individual terms for these 3 series and then group them based on the power on x, the coefficient on each of those x terms would have this structure here. Okay, so we've done a lot of modification, we've worked a lot of algebra. So what's our next step? The idea behind this next step is exactly the idea that I was trying to convey when I was discussing that quadratic equation earlier. In the case of the quadratic equation, we said that in order for an equation, some polynomial equation, or we've got a polynomial set equal to 0, in order for that to be true on an interval of x values, as opposed to just isolated x values, then we need all of the coefficients in the polynomial to equal 0. So utilizing that principle, my next step will be to set all of the coefficients in this polynomial expression equal to 0. Well, what are the coefficients? Clearly I've got these 2 terms out front, and those have to be set equal to 0. But in addition, and sort of more importantly, this entire coefficient expression, remember that every coefficient in the polynomial, there are infinitely many terms in the polynomial, but every coefficient in that polynomial has this same structure. So what I need to do is I need to set this coefficient equal to 0. From this first equation, I see that there's a specific relationship between the very first term, the very first coefficient in my series, and the third a sub 2 coefficient in my series. And then from this second equation, it's giving me a relationship between the n plus 2 coefficient and the n coefficient. Let me rewrite this second equation. Here I first factored a sub n out of these 2 terms, and then I added that term to the right hand side, and then I divided by this coefficient in order to isolate a sub n plus 2. So this expression is a little complicated, but it gives me a relationship, it gives me a method or an algorithm in a certain sense to be able to define all of the coefficients in my series. As I emphasized earlier, the coefficients are what make the series. So if I have a method for somehow computing or determining all of the coefficients in the series, then I have essentially defined the series. And this equation here does provide me with a formula that will enable me to recursively define all of the coefficients in my series. So in this context, it may seem a little strange, but in this context, this type of formula is actually my final answer to the problem. I need to include this initial relationship between A2 and A0 as well, but this really is, in a sense, the answer to this problem. That feels very abstract and a little strange. This is very different than the types of solutions we're accustomed to getting. So just to get a better feel for what's actually going on, let me explore the first several coefficients that are defined by this pair of relationships. My first coefficient, a sub 0, cannot be determined by these equations. There's no way to identify or specify exactly what a sub 0 is. The same is true for a sub 1. If I look at this relationship here, this will allow me to define a coefficient a sub something recursively in terms of the coefficient that was 2 terms prior, right? So a sub n plus 2 can be computed based on a sub n. A sub 1 does not have a coefficient that was 2 terms prior, so it's impossible to use this formula to somehow determine what a sub 1 would need to be. So these first two coefficients can't be determined by these formulas, therefore they have to be given in the problem somehow. So how about a sub 2? Well, we're already told by this boxed relationship here that a sub 2 should be equal to 1/2 a sub 0. But I should also be able to determine a sub 2 based on this boxed relationship. Notice that in order to get the a sub 2 term, I would need n in this formula to be 0. And simplifying that, I actually noticed that I must have made a typo somewhere. So let's scroll back up real quick. Okay, so notice I said we needed to set all of the equations equal, all the coefficients. So this first equation should have actually said 2 a sub 2 plus a sub 1, plus a sub 0 equals 0, which would then imply that 2 a sub 2 equals negative a sub 0. Therefore, a sub 2 equals negative 1/2 a sub 0. And that does, in fact, agree now with this calculation that I got using this formula here. Let's try a sub 3. Notice that in order to calculate the a sub 3 term according to this formula, n needs to equal 1. I'm not going to actually write out, well, I guess I will. So there's the value that I'll get if n equals 1 in my formula. Simplifying that, I get this expression here. And I've actually chosen to leave the denominator as just 3 times 2. I think you'll see why as I work through a few more coefficients. Let's try a sub 4. So here I have an expression for a sub 4 in terms of a previous coefficient a sub 2. But if I back up and look at a sub 2, I've got an expression for a sub 2 in terms of even further prior coefficient, namely a sub 0. So I could make that substitution in here for a sub 2, and that would give me this expression here, which is slightly more advantageous because it is in terms of a sub 0. As we've already pointed out, a sub 0 is going to be some value that has to be given to me or will just remain unknown. And so I can calculate a sub 4 directly in terms of that given value or that unknown value. Let's try something similar for a sub 5. Here I have an expression for a sub 5 in terms of a sub 3, but if I back up a couple lines, I have an expression for a sub 3 in terms of a sub 1. Making that substitution, I now get an expression for a sub 5 in terms of a sub 1. I've been working through these first coefficients in kind of a lot of detail just to make sure that this process is clear. Let me try a couple more, a little bit more quickly, and then I'll see if I can start to identify a pattern for the expression for these coefficients. So I was able to compute expressions for a sub 6 and a sub 7 once again in terms of a sub 0 and a sub 1 respectively, and I'm starting to notice a pattern to these computations. So for example, all of the even coefficients are negative, and the denominator in each even coefficient just looks like the index factorial. Actually, that denominator rule seems to be true across the board. A sub anything will always be that index number factorial. Then how about my numerators? My numerators are a little bit stranger, but they are still pretty predictable. They appear to be a product, but not of sequential integers like a factorial, but they appear to be a product of every other odd number. Utilizing this pattern, I think I can identify a sub 8 and a sub 9 pretty quickly. And at this point, instead of continuing to compute specific coefficients, I kind of want to take a step back and see if I can put all of this back into the context of the solution of my differential equation. So now, just to help make some sense of this a little bit, let me go ahead and group the a sub 0 terms, or the terms that have a sub 0s in them, and then let me group the terms that have a sub x in them. Here, first let me just color code those. So as we've already pointed out, all of the even powered terms will have a sub 0 in the coefficient, and all of the odd powered terms will have a sub 1 in the coefficient. So again, I'll group those and then factor out those coefficients. And I want to go ahead and just leave my final answer in this form. I'll actually, just to clarify, typically I won't even do all of the extra steps that I've done on this page. Since this is our very first example, I kind of wanted to go through some extra detail here. But typically the answer in the green box, the equation that determines or that allows me to compute these coefficients, is essentially my final answer for this type of problem. But in this particular first example, I wanted to push it a little bit further, and just a couple things I noticed about this structure. First of all, we've got a general solution y, which is written as some constant times a function plus another constant times another function. So actually, if we think back to chapter 3, where my general solutions had the form c1 times a function and then c2 times a function, this has that same structure. And that's not a coincidence. And as I pointed out previously about a1 or a sub 0 and a sub 1, those are terms that have to be provided. So as you can see here, those in a sense are acting like the constants C1 and C2, which allow me to accommodate initial conditions if they are provided. And I admit it may feel a little dissatisfying to leave our answers in this form here. In some cases, these series that we have as sort of the two separate solutions are identifiable as some functions, much in the way that we did last section, where we were able to pick out the series representation of e to the x, say, or cosine of x or sine of x. In this particular case, I don't recognize these series as any known functions. Nevertheless, this is a valuable structure or form to my solution, because while I don't necessarily have the full explicit solution, if I wanted to approximate a solution to this differential equation, I could simply utilize as many of these polynomial terms as would be appropriate. And as I pointed out in the previous section, this is a really common technique, and there's lots of contexts in which you can attain the necessary level of accuracy by only using 3 or 4 of these polynomial terms. So again, I admit that this feels like a strange form of our solution, but it can in fact solve the practical needs of a specific problem, because it enables me to identify an approximation of the actual solution by just grabbing as many of these polynomial terms as necessary. Okay, that problem was quite a doozy, and I did in fact need a little bit more room to get in all the detail that I wanted. I really poured a lot of detail into that first example, and so with the subsequent examples, I probably won't go through all of the steps with the same level of detail and explanation. That said, let's go ahead and take a look at the next example.